Hi guys. Today, the next couple of days, we're going to be talking about the next section in our book. So it's the section 2 on electric current from chapter 15. 15.2, we're going to be talking about electric current. So electric current is the flow of electric charge. So in solids, this is the flow of electrons from place to place, and in liquids, it's the flow of ions. So electrons are just that little, it's one of the subatomic particles in an atom that is negatively charged. So those are moving around. And then in liquids, it's ions. So it's those atoms that have extra electrons or extra protons, or they're basically just imbalanced atoms. So then those atoms move around and flow with electric current. So we use the unit of amperes to measure electric current. So for flow and for current, there needs to be a continuous loop to create a circuit. So I have a couple pictures here on the PowerPoint. I also drew one. I don't know if we'll be able to see it very well. Oh yeah, you can kind of see it. Okay, so we'll talk about this in a little bit more. But if you want to look at the ones on the PowerPoint, let me see if I can get a pointer. Nope, we're not going to worry about that. But here you have, this is a battery, and we'll talk about batteries a little more in depth, but basically a battery has power in it and helps these circuits to work. It's a source of voltage. And then we have some wires, and then there's lots of different things that you can have in your circuits. But when we're basically talking about them, a lot of the examples we'll look at have a light bulb. So there is a continuous loop here, but then here you see there's a switch, and so that breaks the loop. So we'll talk a little bit more about that. But a circuit is basically you have to have a continuous loop of electricity. So in this one, let's look at this one. This is a better example. This one, the electrons flow from the positive end of the battery down around, they go to the light bulb, they go into the light bulb and continue going through the wire. There's a little filament there, which is what changes the electric energy into light and heat energy. There's a little bit of a change there. And then electricity keeps flowing down here, down into this negative side of the battery. So this is a circuit. It's a continuous loop. So like I said earlier, a switch will either make or break the circuit. So that's what a light switch or any sort of other switch can turn it on or off, right? That it either turns it on and connects the circuit or turns it off, so it breaks the circuit. So I'm going to get used to this because this is backwards. But here I drew a circuit. So this here, I'll look at it. This is the positive end of our battery. And the little electrons are going to flow. So this is my little electron. It's going to flow around. And then it'll go up into our little light bulb and go down. And it'll keep flowing through. If this is closed, which means that this is a continuous, it continues all the way through, then the electricity will keep flowing. But as soon as that's open or broken, then it'll stop. Then our circuit is no longer continuous, so it will not flow. Yes. So let's go to the next slide. Voltage. So voltage is potential electric energy, and we measure it in volts. So voltage will increase when there is more if voltage increases, more electric energy is available. So if you have a bigger or a different battery, a battery with more voltage, more energy is available. So a car battery has a lot more energy available than just a battery that you put in a flashlight or something like that. So if the voltage increases, more electric energy is available. And then this electric energy is transformed into other kinds of energy. So in this last example, the one that we looked at here on the whiteboard as well, the voltage is changed from an electric energy into light and heat in a light bulb. in other machines or different things, it can be kinetic energy, or I'm trying to remember what other kind of heat, thermal energy. So voltage. So, so going back to this, the current flow. So one electrons, because our wire is a solid, right? So we're going to use electrons will flow versus ions. So when we're looking at this, one electron doesn't go, it's not like there was one little tiny electron and he like travels all the way through, lights up the light bulb and keeps traveling. That's not how he can't travel that fast. He doesn't go that fast. He doesn't typically make it all the way around the circuit. What happens is this little electron bumps into another electron, which bumps into another one. And these keep bumping and they keep pushing this energy along. They keep pushing it along, going further and further and further around our circuit. Okay? So they're moving, bumping into each other, moving the next one forward, and passing that electric current to flow, or like getting that electric current to flow. So it happens like the bumping into and moving towards the positive part of the battery or power source happens trillions of times each second. So batteries, this little bad boy right here, there's a chemical energy in here that turns into potential energy. So the chemical energy is found within a paste. So in batteries, let me just make sure that I'm drawing my picture right. So this is our positive end, and there's like inside the battery, there's like this moist paste that has chemical energy in it. Okay, so there's some there's different chemicals in here. And I think if I write it, can you see it? Oh, you can read that. Okay. So there's different chemicals in here, and they go through different reactions that give off energy and move electrons from the positive end of the terminal to the negative end of the terminal. Okay, so it's constantly moving electrons down here. Okay, which also makes them want to move this way as well throughout the circuit. But batteries, this chemical, once this chemical reaction takes place, there's a different chemical, it's a different compound present. So once this, it gets used up and it turns into something different, maybe I'll try a different color. Let's try a different color. So as it's going through these different chemical reactions, it changes into something else. And it's used up. Oh, that's dead. Good. So it changes. We use more of the battery. We use more of that energy. It changes. We use more of it. It changes. And eventually this chemical energy is used up, and then our battery is dead. There's no more of the substance, the little paste that was in there, to be able to have those chemical reactions that cause the electrons to move. So then it stops. It is dead. It doesn't work anymore. There's no more potential energy in here. All of it has been used up into actual energy has been moved into electrical energy. So when there's no more of the chemicals left, the original chemicals left, that's when we would consider the battery dead. Ooh, good. Resistance. I forgot where I was going next. Okay, so resistance. So in the last section, we learned about conductors and insulators. Take a minute, think about those. What's the difference between those? Okay, so conductors, they make electrons flow easily, but not perfectly. So there's a certain degree of resistance that makes it more difficult for electrons to flow. So it's not like, I'm trying to think of an example. It's not like sliding down a water slide, because the water makes it so much easier, so much faster for you to go. It's like going down a normal slide of like, yeah, you might get stuck or it might be not as slow. Like that's why a water slide is typically more thrilling than a normal slide, because you can go faster because there's less resistance. So resistance, we measure in the unit of ohms. And that looks like a little, I think the omega is what they call it. It kind of looks like a little horseshoe kind of guy. I think they have it in your book when you're doing your guided notes, if I have you do those. But it kind of looks like that little guy. So copper is something that we use very commonly for wires because it has little resistance. It allows things to go really easily, okay? It allows the little electrons to move, to bump into each other, to push each other forward, to go really fast. But if there's a greater amount of resistance, there's like a greater amount of friction of sorts. And so that can cause wires and different things to heat up. So if our slide was made of like sandpaper, that would like hurt, and it would probably be like hotter like as you're going down, because there's that friction that is causing resistance and like will cause it to heat up. So just like that example, resistance in wires, so the resistance of electrons flowing within wires can also cause heat and that thermal energy, and that can be dangerous. Like we don't want our computers overheating, right? We don't want these other electronic appliances overheating. We want them to work. So it's important to use conductors with little resistance. So yeah, resistance not only is dependent on like the material, but also the length and the thickness of a wire. So let's say if you, I'm trying to think. So if you're trying to draw, let's say you're racing. If you run the 100-meter dash, you're going to get like kind of warm, kind of sweaty. You'll be out of breath, right? But if you tried to run a 400-meter dash in pudding instead of just on the normal track, that would cause a lot more resistance, and you would be a lot more tired and worn out and probably like sweaty and warm by the time you finish running that race. So just like the thickness and the length of of wires can have an effect on the resistance. So the wider and shorter a wire is, the less resistance there is. So if it's thicker, there's more room for the electrons to move. There's more space for them to bump into each other to move. So there's less resistance. And if it doesn't have to go as far, there's less resistance as well. That's all for this section. I'm going to try to make another video for the next section. I hope and pray that this helps and doesn't make it more confusing. If you have questions, please let me know. I'm happy to help anytime. Let me know. I think that's all for today. Have a good one.